Om Namah Shivaya. A very warm evening to everyone. It gives me immense pleasure to welcome you all to day 3 of the AICTE sponsored ATAL online 6-day faculty development program on semiconductor for smart systems, applications in IoT, AI, and next generation devices, organized by the Department of ECE in association with IQAC and IIC of Sri Satyam College of Engineering and Technology. The theme for day 3 is embedded and intelligent integration, which plays a crucial role in enabling energy efficient, intelligent IoT systems. Today, we are privileged to have two eminent industry experts who bring rich technical expertise and practical experience in low power embedded systems and semiconductor based sensor integration. We look forward to an engaging and insightful evening. Let us now commence with technical session 5. To formally introduce our distinguished expert for technical session 5, may I now invite Dr. S. Mahendran sir, Head of the Department of Electrical to introduce the research.
Sir, am I audible, sir?
Sir.
Good evening to one and all gathered here. It is my pleasure to introduce our today's chief guest, Dr. A. Madhivannan, an accomplished embedded software engineer, IoT developer, and a technical trainer at One Modo Technologies, Chennai. With dynamic expertise in artificial intelligence and machine learning driven embedded systems, IoT solutions, and applied R&D, he has worked on projects ranging from real-time face recognition and automated way bridge systems to NLP-based chatbots and IoT-enabled safety and automated solutions. He is proficient in embedded C and Python, including MicroPython, NLP, OpenCV, PyTorch, and scikit-learn, and has extensive experience with ARM, STM, ESP, and Raspberry Pi platforms. His R&D interests include IoT security, embedded AI for ML, and intelligent vision systems. And he has guided numerous internships and training programs, bridging the gap between academy and industry. We are indeed delighted to have him with us to share his insights on low power design techniques for edge devices, a topic that lies at the heart of efficient IoT systems. Sir, we are eager to listen to you, your session. Thank you. Thank you for the opportunity given to me.
So thank you, Dr. Mahendran sir, for the wonderful introduction of our expert. Now, with great pleasure, I invite Engineer A. Madhivannan sir to deliver his session on low power design techniques for edge devices. Sir, the session is yours.
Thank you, sir. Thank you for the introduction.
Yes,
Is it
sir?
visible, sir?
Yes, sir. Your screen is visible, sir. So kindly check whether your slides are moving or not, please.
Sure, sir.
Yes, sir. It is moving, sir. You can proceed, sir. Please.
Thank you, sir. Thank you, sir.
Good evening, everyone, and welcome to today's technical session on low power design techniques for edge devices. Before that, let's first clarify what we mean by IoT devices and edge devices. Let's take an example from smart agriculture. Imagine a soil moisturing monitoring node. In a traditional IoT setup, it might send readings to the cloud every few seconds. But in an edge computing model, it processes the data locally, say, let's say for example in an ESP32 or STM32 microcontroller. What it will do is it transmits data only when the moisture level drops below a certain level. So we can set up the threshold for which the level that can be on ourselves to process the exact system to send the exact data at the same timing. So what it will do is it will reduce the communication energy and improve the efficiency and also including devices lifetime. Here, we will be covering in this session the complete life cycle of building a low power IoT edge device from hardware design to system level optimization. So, the topics we are going to cover first of all low power hardware design, then we are going through power consumption edge devices and power management strategies, communication protocols, and finally energy harvesting techniques. Why low power? Now, why do we focus on low power? Most IoT and edge devices are deployed in remote or hard to reach environments. Industrial machinery, bridges, agriculture fields, or even on our bodies as wearables. These devices often rely only on batteries or ambient energy harvesting. Consider a simple example, a temperature sensor node that consumes 500 milliwatts continuously. The goal of a low power design is to maximize device lifetime while maintaining performance. To achieve this, modern IoT devices process data locally instead of sending every bit of raw data to the cloud. Why? Because wireless communication is by far the most power hungry operation. In fact, sending a single Wi-Fi packet can consume as much energy as thousands of microcontroller operations. That's why today's design focus on local intelligence, event-driven sensing, and adaptive communication to make systems not only smarter but also more power efficient. So let me look at main power consumers in edge devices: sensors, processing units, and memory. So what are sensors really? These are the device's eyes and ears, continuously sampling environmental parameters like temperature and motion. For instance, the LM35 temperature sensor draws about 60 microamps, while a PIR motion sensor consumes about 100 microamps when idle and 500 microamps when active. To save power, we use adaptive sampling, only increasing sensor activity when meaningful changes occur, and choose ultra low power sensors like BMP180 or DHT11 for battery powered systems. So, what are the processing units? Those are the microcontroller units and AI accelerators. Devices such as the ESP32 or STM32 or ARM Cortex M7 act as the brain handling sensor data, signal processing, AI inference, and data compression. Active computation significantly consumes energy. To reduce this, we apply duty cycling, dynamic voltage, and frequency scaling (DVFS for short) and streamline the code and algorithms. And let's come to memory. Those are the flash and DRAM. Writing data to memory consumes energy, roughly zero point 0.1 millijoules per kilobyte. Imagine a node logging 10 kilobyte per minute. That's roughly 1.4 megabytes daily or over 1 joule of energy. To conserve energy, we reduce write frequency and use compression or bulk writes buffered in RAM. And those communication radios are notorious energy hogs. Wi-Fi transmission draws about 660 milliwatts, whereas LoRa operates at low power, roughly 132 milliwatts, but only in short bursts. Therefore, optimizing communication protocols and minimizing transmission frequency through smarter local processing are essential for longer device lifespans. Let's see a working example right now. Let me share a practical example, a smart vibration monitoring node. This node uses a MEMS accelerometer consuming roughly 3.3 milliwatts. Combined with an ARM Cortex M4 MCU that performs FFT analysis, the MCU runs at about 16.5 milliwatts duty cycle around 20% of the time. It logs data to flash memory and uses a LoRaWAN radio for anomaly transmission. The total daily energy consumption is around 0.47 watt hours. Sorry, I made a mistake that about 0.37 watt per day in the presentation. I hope you are not worried about that. It logs data to flash memory and uses a LoRaWAN radio for anomaly transmission. The total daily energy consumption is around 0.37 watt hours. With a 2000 mAh 3.7 volt battery of approximately 7.4 watt hours, the node can run for roughly 15 to 16 days continuously. But by intelligently transmitting data only on anomaly detection, runtime can be extended to 6 months or even a year. Now let's talk about power management strategies. One of the most crucial aspects in edge device design is power management strategies. Every IoT or edge device operates under strict energy limitations, often running on small batteries or sometimes relying on harvested energy. So our goal as an engineer is to make every milliwatt count. There are three cornerstone techniques that dominate low power hardware design: dynamic voltage and frequency scaling (DVFS), clock gating, and power gating. Power management happens at multiple layers of the system, not just in hardware. At the hardware level, techniques like transistor optimization, DVFS, and power gating control how circuits physically consume energy. At the firmware level, we manage sleep scheduling, peripheral control, and even adaptive voltage regulators that fine tune voltage in real time. And at the system level, we handle intelligent task scheduling, predicting workloads, clustering operations, and even offloading computation to the cloud when that's more energy efficient. If we look at the power equations, where the total power is equal to capacitance times voltage square times frequency added by the current that is lead multiplied by the voltage again. This tells us that the total power has two major components: dynamic power, which depends on voltage, frequency, and capacitance, and the other one is leakage power, which depends on the leakage current even when transistors are idle. Our task as designers is to control all three: the voltage, frequency, and active components dynamically so the device only uses the energy it truly needs. This layered approach ensures that power savings happen everywhere from the transistor all the way to the application software. So, let's talk about dynamic voltage and frequency scaling. Let's dive deeper into this first strategy. Dynamic voltage and frequency scaling allows a processor to adjust both its supply voltage and clock frequency based on its current workload. When the processor is busy, such as performing image recognition on an edge AI node, it operates at a higher frequency and voltage. But when idle, it can slow down the clock and reduce voltage. The dynamic power consumed by a circuit is given by the following formula. Here we can see that the power varies quadratically with voltage, meaning that a small reduction in voltage gives a huge power saving. For example, in an STM32H7 microcontroller based on the ARM Cortex M7, adaptive PLL scaling allows the clock to adjust dynamically for industrial control applications. By reducing voltage from 3.3 volt to 1.8 volt, we can cut power consumption by nearly 70 to 80% while maintaining performance for moderate workloads. DVFS is widely used from mobile phones to smartwatches and now even in edge AI processors and IoT nodes because it gives a perfect balance between energy efficiency and performance. Next, we have clock gating, one of the simplest yet most effective ways to save power. Every logic element in a microcontroller consumes power. When the clock signal toggles, even if the circuit isn't doing useful work, so the idea is simple: turn off the clock to modules that are idle. There are several implementation methods: fine grained gating, coarse grained gating, and silent water. Fine grained gating, where we disable clocks to individual registers or pipeline stages. Coarse grained gating, where entire peripherals or functional blocks like ADCs or UARTs are gated off. And with modern design tools like Silence Vivado or Synopsys Design Compiler, we can even automate this clock enable logic. Firmware can also manage this directly in STM32 or ARM Cortex M controllers. We use RCC registers to enable or disable peripheral clocks. This technique alone can provide 20 to 40% reduction in dynamic power, and it's almost always the first optimization step in low power design. Think about a smartwatch. Most peripherals, Bluetooth, sensors, ADCs are asleep most of the time. Clock gating ensures they consume zero active power until needed. Finally, let's look at power gating, the heavyweight technique for eliminating static power. Even when circuits are idle and clocks are gated, transistors leak a small current known as leakage. Over millions of transistors, this leakage can still drain the battery. Power gating solves this by using sleep transistors, essentially electronic switches, to completely disconnect power from unused sections of the chip. The leakage power is given by the below formula. To ensure data is not lost when a block is turned off, we use state retention cells, isolation cells, and header footer power switches. A great real world example is the STM32L4 and L5 microcontrollers, which implement stop and standby modes that fully power gate both the CPU and its peripherals. This achieves a leakage reduction of 80 to 95%. When the device wakes up, the retained state allows it to resume operation instantly, perfect for IoT nodes that may sleep for hours but need instant response when triggered. So in start, in short, clock gating handles dynamic power and power gating attacks static leakage, together forming a complete low power strategy. Moving on, let's discuss energy harvesting techniques, which are the core of sustainable self-powered IoT systems. Energy harvesting allows devices to scavenge ambient energy from their environment, reducing or even eliminating the need for conventional batteries. The main approaches we focus on today are vibration and thermal energy harvesting, power conditioning, and energy storage, RF and hybrid energy harvesting systems. Vibration and thermal energy harvesting, converting mechanical motion or heat into electricity. Power conditioning manages harvested energy efficiently and storing it to practical use. RF and hybrid energy harvesting systems capture the energy from ambient electromagnetic signals or combining multiple sources for continuous operation. These strategies are essential for enabling long lifetime maintenance free IoT devices, wearables, electronics, and industrial sensors. Vibration and thermal energy harvesting. Let's start with that. Vibration or piezoelectric harvesting works on the principle that mechanical strain in piezoelectric materials generates electrical charge. The power harvested can be expressed as half of capacitance times voltage square times frequency. On the other hand, thermoelectric or pyroelectric harvesting leverages a Seebeck effect, where voltage is induced by a temperature gradient. Voltage is directly proportional to alpha delta T. Here, alpha is the Seebeck coefficient. Applications include industrial exhaust monitoring and wearable devices that harvest body heat. Essentially, any thermal differential becomes a source of energy. Next, we have RF and hybrid energy harvesting. RF harvesting converts ambient electromagnetic signals into DC power using a rectangle, a combination of rectifier and an antenna. Typical sources include Wi-Fi at 2.4 GHz, GSM at 900 MHz, LoRa at 868 MHz, and FM radio at 100 MHz. Depending on the source and distance, harvested power ranges from 10 microwatts to 1 milliwatt. For example, a smart batch can intermittently power an NFC tag using harvested Wi-Fi signals. Hybrid energy harvesting systems combine multiple sources such as solar, vibration, and RF to ensure continuous energy availability. This approach mitigates the intermittency of individual sources. For instance, an industrial bridge sensor could use solar energy during the day and vibration from traffic at night, resulting in over 10x improvement in device lifetime. Finally, let's look at power conditioning and energy storage, which is critical for making harvested energy usable. Power conditioning modules include boost converters, MPPT controllers, and AC to DC rectifiers. Boost converters step up low voltages, sometimes as low as 100 millivolts. MPPT controllers dynamically track the optimal operating point to maximize energy extraction. AC to DC rectifiers, essential for converting AC signals from vibration or RF into usable DC. Energy storage options are equally important too. Supercapacitors provide high cycle life and rapid charge discharge. Thin film batteries, solid state microcells, offer stable long term energy storage. The hybrid storage combines capacitors for burst loads with batteries for sustained operation. Together, these technologies enable batteryless or battery assisted IoT nodes which can operate for years with minimal maintenance. This is a game changer for distributed sensor networks, wearable devices, and industrial monitoring systems. Let's look at low power edge AI processors, a critical enabler for real time intelligence systems at the edge. Topics we'll cover here will be need for low power edge AI processor architecture, computation and memory reduction, power management in AI accelerators, tiny ML, micro AI, and industrial. The need for low power edge AI. Why do we need low power edge AI? Traditional cloud inference consumes over 100 watts and introduces high latency, which is unacceptable for real time applications. The goal of edge AI is to perform inference locally with less than 1 watt, enabling devices to make decisions instantly, reduce reliance on the network, and improve privacy. The total energy consumed by AI can be represented as the below formula, where E total is equal to E computation energy and multiplied by, added by E memory access energy and E to the communication energy. The focus, therefore, is on reducing all three using hardware algorithm co-design, ensuring that computation, memory, and communication are optimized altogether. Let's explore the architecture of edge AI processors. Modern edge chips are often heterogeneous SoCs integrating multiple specialized units. CPU for handling control logic and data preprocessing. NPU, neural processing unit, accelerates CNNs and machine learning inference efficiently. The design features include multi-voltage domains to enable DVFS, on-chip SRAM caches to reduce energy-intensive DRAM caches, dedicated MAC arrays for high-efficiency matrix operations, on-chip SRAM caches to reduce energy-intensive DRAM accesses, dedicated MSC arrays for high-efficiency matrix operations. A practical example is the NXP IMX8M Plus, which delivers 2.3 TOPS of NPU performance at under 1 watt, demonstrating that high AI throughput is possible even at ultra low power. To achieve low power operation, algorithm level optimizations are key: pruning and quantization. Pruning removes 60 to 80% of redundant bits, reducing both computation and memory, wherein quantization converts model bytes to 8-bit or 4-bit fixed points, saving memory and enabling faster arithmetic. Terna- Ternarized backpropagation replaces multipliers with simple logic operations, lowering energy use. Knowledge distillation. Smaller student models learn to replicate larger teacher models, maintaining accuracy with fewer resources. These strategies combined with efficient hardware make it possible to deploy high performance AI on edge devices, from microcontrollers and wearables to industrial IoT sensors. At the core, we see three memory layers: boot code, parameters, read only configuration. Boot code and FOTA, firmware over the air. This is the top layer responsible for fast wake-up and secure boot code download. The design ensures that the processor can initialize quickly and supports fast OTA changer updates, which minimizes power consumption during firmware updates. Parameters and data log. This middle layer stores operational parameters and logged data. It is flexibly managed at the byte level, allowing selective reads and writes, which reduces unnecessary memory access and saves energy. This approach is critical in edge devices, where every byte read or written contributes to the energy budget. Read-only configuration. The bottom layer contains safe, immutable configuration data. By making this read-only, the system prevents accidental writes, which enhances both reliability and energy efficiency, since write operations are far more costly in power than reads. Surrounding these layers are additional optimizations. Ultra low power operation, the system is designed to operate with the minimal energy budget both for read and write operations, enabling years of battery free or maintenance free operations in IoT devices. Fast wake up and boot, the device can resume operation almost instantly, which reduces the idle power spent during startup. FOTA fast upload mode. Optimized firmware updates, which reduce network time and processor load, minimizing energy consumption. Flexible byte management allows partial memory access instead of reading or writing entire blocks, which is key for reducing memory access energy. Safe read only data access ensures that critical configuration is always secure and avoids unnecessary write operations. In essence, this architecture combines layered memory management with hardware software code design to achieve high reliability, security, ultra low power operation, all essential for memory optimized edge AI and IoT devices. Looking at all this, there is a crucial area for achieving efficient edge AI. First, dynamic voltage and frequency scaling or DVFS. Here the processor dynamically adjusts its voltage and frequency according to the workload. Next, we have clock gating and power gating. These strategies essentially turn up ideal computation units and control logic. Now let's talk about TinyML, which is really transforming AI at the edge. TinyML refers to ultra lightweight machine learning models designed to run on microcontrollers with less than 1 MB of RAM. It's incredible that we can run AI tasks on such minimal hardware. Some popular frameworks enabling that these are TensorFlow Lite Micro, CM6NN, and Edge Impulse. Finally, let's look at the power consumption ranges. A tiny ML microcontroller unit consumes less than 100 milliwatts, and AI SoC like HTPU uses under 2 watts, while platforms like Jetson Nano range between 5 to 10 watts. This illustrates the huge potential for energy efficient AI at the edge, enabling applications from battery powered IoT devices to smart sensors in industrial environment. So, in summary, combining intelligent power management with tiny ML allows us to deploy AI in a way that both powerful and extremely energy efficient. Let's start with communication protocols for low power IoT, a cornerstone of energy efficient industrial systems. An IoT communication power often dominates total energy consumption, especially in wireless edge devices. Our goal is to minimize energy usage while maintaining reliable connectivity. To achieve this, we look at low power communication standards, energy efficient communication techniques, and power management in AI accelerators. So, in essence, low power communication coupled with HAI is the key to sustainable and scalable industrial IoT networks. Let's focus on communication power in IoT. Our objective here is simple: reduce power consumed during wireless data transfer between edge devices and the cloud. The energy consumed in transmitting data can be calculated as the below formula. This shows that transmission power dominates total system energy, often more than 70%. However, there are challenges. Continuous connectivity drains batteries quickly, and we must balance range, data rate, and power. So, what are the design goals? Low duty cycle transmissions, adaptive modulation and data aggregation, efficient MAC scheduling. For instance, consider temperature sensor in a smart building. By aggregating hourly readings and transmitting them in a single packet, it reduces transmission energy drastically compared to sending data every minute. These are the low power communication protocol standards from Bluetooth to Wi-Fi Halo. Bluetooth is ideal for short range, whereas Wi-Fi Halo bridges the gap between low power and high bandwidth needs, supporting moderate range with substantial data rates, making it appropriate for video surveillance and other applications requiring higher throughput. When selecting a protocol, one must carefully consider trade-offs around range, data rate, power consumption, and the deployment environment to optimize device performance and longevity. Finally, let's explore energy efficient communication techniques that complement these protocols. Duty cycle MAC, adaptive TX power control, data aggregation and compression, wake up radio, packet scheduling, and cluster based routing. The average power consumption can be modeled as the below formula, where D is the duty cycle. By reducing D, we can save significant energy without affecting performance. For example, in a smart factory, Vibration sensors using duty cycle math and data aggregation can operate for months on small batteries, all while maintaining real-time monitoring for predictive maintenance. To wrap up, low power design is the bedrock of a sustainable intelligent IoT future. We traverse through sensor selection, MCU workload optimizations, DVFS, gating techniques, energy harvesting, local AI inference, and communication protocols. The future is not just connected, it's intelligently efficient. Efficient energy design isn't just optimization, it's the foundation for a sustainable intelligent IoT future. Thank you.
So thank you, sir, for your highly insightful and practically relevant session. To deliver the vote of thanks for this session, may I now invite Professor M. Prasidarthi, Head of the Department of Artificial Intelligence and Data Science, to address the gathering.
Thank you very much, Engineer Madhivanan, for your highly insightful and practically oriented session on low power design technique for edge devices. Your clear explanation of low power design skills such as clock gating, voltage scaling, and power management combined with your real world experience, a sincere gratitude to you for accepting our invitation and sharing your expertise with us this evening, sir. Thank you once again, sir.
Okay, thank you, madam, for your kind words and for proposing the vote of thanks so gracefully. I request all the participants to stay online. We will have the technical session 6 sharply at 7:30 p.m. Before that, I have to share the today's feedback session about the technical session 5. If you want to make any queries to the resource person, I will share the details of him through our chat box as well as WhatsApp group, please. It's my pleasure to introduce Ms. Vaishnavi Dinesh, the founder and CEO of Towards Technology, a technology-driven enterprise delivering AI-based smart solutions across diverse domains. Ms. Vaishnavi holds a bachelor degree in robotic and automation from PSG College of Technology and a master degree in instrumentation and control systems from Shastra University. She brings over 5 years of industrial and 7 years of academic experience, making her a true bridge between innovation, research, and real-world applications. Under her leadership, Towards Technology has become a hub for AI, embedded systems, IoT, and industrial automation, collaborating with academic institutions and impact over 10,000 learners through hands-on training, boot camps, and workshops. We are delighted to have her with us to share her expertise on semiconductor-based sensor integrations for IoT devices, which plays a vital role in intelligent system design. Madam, we warmly welcome you for the technical session 6. Thank you, ma'am. So thank you, Professor Sasikumar sir, for the warm and insightful introduction of our expert. Now, with great pleasure, I invite Engineer V. Vaishnavi Dinesh ma'am to deliver her session on semiconductor-based sensor integration for IoT devices. Madam, the session is yours. Ma'am, kindly share your PPT
Sure.
slides, ma'am.
Yeah, very good evening all.
Good evening, madam.
First of all, I thank Sri Satyam College of Engineering for inviting me for this faculty development program. In the 6 days in faculty development program, my topic is semiconductor-based sensor integration for IoT. Before that, I just want to give a short introduction. Already Sir gave it to me. I am a founder and CEO of Towards Technology, and this is the company focused on AI and embedded related solutions. Yeah. Before we go into the topic, I just want to know why semiconductor will be a hot topic in today's world. Any answers? Why it become this much boom in between last 1 year?
Participants are watching your presentation. Okay.
Okay, sir. No problem.
Okay.
Yeah, actually, year before, everyone talking about AI and deep learning, Gen AI, like that. And suddenly we are going to the semiconductor. Do you have any idea why we have this shift? Fine. We all know one of our ministers will talk in our launch. They talk about all the startup in India should focus on AI and semiconductor, like that he told. After that, everyone search about semiconductor. Why this is this much important? And the importance of semiconductor will get a boom, and everyone speak about the semiconductors. Semiconductor play a important role in modern electronics. Whatever the electronics we see around us, from laptop and our mobile, then any other AC, fridge, whatever the thing we are seeing, from home application to industry application, everything is a electronics. Beside electronics, it's a basis semiconductor. We have many materials like aluminum, copper, wood, rubber, everything will be a material, right? But silicon is much more different, and it will be very unique. Why? Because if I take a wood and pass a current, it will not allow the current, it just stop it. Wood, rubber, anything. And if I take a copper or aluminum, it just pass the current, it freely go through it. There is no restriction or anything, it just pass it. But if I take a material like silicon, gallium arsenide, and germanium, it can have a certain condition. When the current should pass, how much the current should pass, when it should be stopped, those things will be done. Because of this unique property, the semiconductor have been made by using silicon, gallium arsenide, and germanium. Then, why this become this much famous? Because of this unique property, we can control when to pass the current and how much current would pass. Those things we can control. Then, because of this unique property, many elements, many components are risen. The first thing is diode. We all know how the basic electronic component will be a diode and transistor, and the recent technology MEMS also based on semiconductor. In transistor, it just act like a switch. We can use it as a switch. We just make the current electricity on and off by using the transistor. And in MEMS, we can do many things. We can control applications. We can able to make decisions and all. So from a basic component to recent component like MEMS sensor, semiconductor is a base. Then semiconductor will act as a brain. By using this semiconductor, we can do a magic in the world. Whatever the innovation we found, it's all the basis semiconductor. AI technology will be arise, I think, in 1930s and 1940s. But at that time, that will not reach many people. Only last 20 years, we have this much boom. One of the main reasons we have developed electronically strong. We have many CPU and GPU and TPU in our system. Because of this highly strong processing power, they will give a boom. It will give a magic. Whatever the thing you want to do, we can do it like in AI. For example, ChatGPT, one of the best example. Just imagine if the processor is not that much good. We don't have GPU and TPU. Can you able to chat ChatGPT with this minimal time, and at a time many people are chat with ChatGPT and we get a immediate response? It's not possible without this innovation. So semiconductor plays a major role. Even AI also depend on this semiconductor growth. AI parallelly grow. After a few days, what we do is we just forget the semiconductor and we'll speak about AI. But semiconductor is the base for a boom of AI also. Then, our topic is sensor integration for IoT. First, we'll discuss what are the types of sensor available.
Ma'am, kindly turn on your camera 10 minutes once, please. We want to take the photograph.
Okay,
okay.
sir. Next, we just see what are the types of sensors available. First one is semiconductor sensor. We already discussed. Semiconductor sensors can able to make decision by its own. We can see in our mobile, we are using many semiconductor sensors inside our mobile. Next one is electrochemical sensor. Electrochemical sensor help to measure some chemical parameters. For example, if you want to measure the food quality or water quality, at that time we can go for an electrochemical sensor. Next, optical sensor. Optical sensor work based on by measuring the light wavelength and light intensity. Based on that, it converts that signal into the electrical signal. Next, mechanical sensor. Mechanical sensors are huge. Mechanical sensors are huge, and it help to measure some mechanical parameters like force, pressure, vibration, and those things. Next, I just want to ask a question. Just take an example of smartwatch. If you are going to buy a smartwatch, what are the things you are consider? I just want to buy a smartwatch. What are the things I have to consider?
Whether my
First,
touch,
yeah, ma'am, please.
whether my touch screen input
Yeah,
is
okay.
working.
My touch screen will be better. If I click some message or contact button, it will respond immediately. We have to check then what are the parameters we consider. Next thing is we have to first think whether the watch will be lighter weight or not. Because that is very important. We have to put the watch for a whole day. It should be a lighter weight. Then it should have a low power consumption. If I put a charge for my watch, it have to be come for 2 days or at least one full day. That is one more consideration. And it will be fast, as usual, ma'am said. If I click some buttons, it should open instantly. Those things I have to consider. Here, many sensors are available: semiconductor sensor, electrochemical sensor, optical sensor, and mechanical sensor. Each are best in their own way, but semiconductor will be very good for IoT-based application. Why? Because if I go for an electrochemical sensor, the sensors will give accurate values, but those sensors will interact in a very delay. It takes more delay. If it measures and it converts that to an electrical signal and pass to some other controller or processor something, it will take a considerable amount of time. That will be a main drawback of electrochemical sensor. Then optical sensor. Optical sensor will be good and no delay, but it will be very costly. At the same time, if you are purchasing any product or something, cost is one of the important parameters for home applications. In case if we go for any medical application or any satellite application, at that time, cost doesn't matter. We go for a precise measurement. And then the drawback of optical sensor will be, it will be very costly. Then mechanical sensor. Mechanical sensor will be very heavy weight. I already told if I buy a watch, it should be a lightweight. But if I put mechanical sensor, it will be very bulk and it occupies more space. That will be a main drawback. So we go for semiconductor for regular application and interact with IoT. These are the reasons why we go for semiconductor based sensor. First thing is it will be a miniature in size. I can the watch will be in somewhat 5 centimeter or something. In that I can do many operations. I can make a call. I can measure my body parameters, how much BP I have, oxygen I have, then how much distance I can walk. Many sensors in a single watch. We have many sensors. That sensors will be integrated and occupy in that minimal space. And many operations can able to do simultaneously. In watch, I can able to attend a call and I can able to transfer a file. And I can send the data to cloud or through Bluetooth. I can send the data. Those things, if I do this much applications, I need that much components, right? For doing data transmission, I have some Bluetooth module or Wi-Fi module or internet module. And if I want to attend a call or something, I have that GSM support. And for tracking my location, I have the GPS support. Then I measure my body parameters, many sensors like oxygen sensor. For measuring a walk at that particular sensor, many sensors are integrated in a single watch. So it will be a very minimum space only it occupies. That is one of the main reasons. Next one is low power and high sensitive. Here, usually nowadays, the watch will be connected to our drive. So internet will be accessed 24/7 in our watch. If internet access, obviously the power consumption will be more. But the semiconductor, when compared to other sensors, semiconductor will take very minimum power. So one of the reasons for that. Next one is easy integration with hardware. Just We all work with some basic controllers and processors like Arduino, Node MCU, and Raspberry Pi. Whatever the sensors we take, whatever the controller or processor we take, if we take semiconductor based sensor, we can easily integrate with those controllers. We just download a library and data sheet. Based on that, we put a programming and we just connect it easily. In case if you want to connect some other sensor like optical sensor or some chemical sensor, at that time the integration it is possible, but the integration will be a little bit hard when compared to semiconductor devices. Next one is cost. If you are going to buy any product, cost is one of the important parameter. If I produce a semiconductor sensor as a mass quantity, at that time the cost will be more. If I want to prepare a single piece, definitely the cost will be equal to whatever the optical sensor cost, that much cost the single piece will be. But if I go for a mass production, at that time the cost will be reduced. For example, if I buy a Arduino, the cost will be minimum only. If I want to do a ASCII or FPGA devices by my own, if I want to create some unique, at that time the cost will be. So if we go for a bulk production, at that time the cost will be low. So only we can easily able to buy a smartwatch at 2,000 rupees onwards. Next one is multi-sensor integration. Already we discussed in a watch. If I take a watch, in that watch, many sensors are integrated in the. Next, if I take a phone, in phone we have many sensors. We have accelerometer, galvanometer, and inbuilt touch sensor, voice sensor. Many things are available. Those things are easily integrated. For that purpose, we can go for that. Next one is I already discussed that. These are the reason we opt for a semiconductor-based sensor for IoT application and regular users also. We have many advantages. Next, semiconductor technologies. These are the many technologies are there, but I mention one of the famous technologies. First one is MEMS. We are all familiar with this technology. In this, by using mechanical components like diaphragm or some beams, based on that, if you are giving any force or vibration, that thing will convert it to an electrical signal. Okay, those are MEMS sensor. Based on this principle, it will work. This MEMS sensor is a game changer of the semiconductor industry. Maybe it will be used in most of the phones and mainly in automobile industry. The first MEMS sensor will be in real use in airbag of automobile industry. In that only the first MEMS sensor will be implemented. Then next one is CMOS sensor. In CMOS, many photo transistors are connected in a set of array. And based on the light absorption, it will convert the electrical signal. The best example will be camera. Here the CMOS sensor technology will be used. It can capture an image and convert it to electrical signal, and we get an image like that. This sensor will be very cheap. This will be can implemented in drone, laptop, phone, wherever the camera are required at the place, we can go for a CMOS sensor. Next is MOS sensor, metal oxide sensor. Here, this sensor will be based on any one of the conductor like NMOS or PMOS. Based on this, it working. This sensor, it will react with any gas or any other component. It will produce an electrical signal. Based on that, the MOS sensor will be working. Next one is biosensor. The biosensor react with an enzyme or some other biological component. It will convert those to electrical signal. The element inside the biosensor convert those to the electrical signal. These technologies are used for semiconductor sensors. Next one is architecture of IoT in sensor node. This is the architecture. We already well versed about this. Let's take one by one. First is sensing element. That is our sensor. We can use have n number of sensors. Based on our application and need, we can select. For example, if I want to measure temperature, I have n number of temperature sensors. based on my need, whether for my application, accuracy is important, cost is important, delay is important. Based on that, I have to pick a sensor. For example, if I using a temperature sensor for measuring my room temperature, at that time I don't need that much accuracy. So I go for a minimum cost sensor. It will randomly measure plus or minus 2 degrees Celsius will be vary. That will not make a problem. At that time, I can go for that sensor. In case if I go for any, for example, nuclear power plant, in that the temperature maintenance is very important. Nuclear power plant or electric power plant or any food manufacturing industries, in those cases, maintaining accuracy is very important. At that time, we should not worry about the cost. We can go for a high precise giving sensors. Then we can also consider whether we can go for an analog sensor or digital sensor. Next thing, signal conditioning circuit. Whatever the sensors are, it will just accept the physical parameter and convert it to electrical signal. There will be definitely a noise. The noise will be because of our environmental temperature and environmental noise also. Anything, the noise will be happen. And because of even the sensor will be getting very old, at that time, the sensor itself giving some noise. Those things will be rectified here. Signal conditioning circuit is very important because if the signal or some of our data, it will be clear, then only our output will be good. Even our coding will be good and our microcontroller will be in good condition. High costly microcontrollers we used. Even if we are using those things, if the data will not be good, we are not get a perfect output, whatever we consider. So signal conditioning is very important. Then obviously the signal is given is very minimum. We have to amplify that signal and reduce the noise in those signals. Next thing is conversion. We have to convert analog signal to digital signal. Then we have to give it to our microcontroller. In case that option will not be possible, inside the microcontroller, we have A to D conversion. Inside microcontroller, we have to convert and use it for further application. Next one is microcontroller. For microcontroller, we have many options. I will take just a simple example, Arduino and ESP32. Okay. If I take Arduino, I just want to collect a sensor data and store it in a cloud and do some process and will get an output. Based on that, I want to do some changes. This is my full requirement. If I go for an Arduino microcontroller, what happens means, yeah, I can easily connect sensors. We can connect up to 6 analog sensors and 13 digital sensors. If you want some more sensors, we can connect extra modules and access more sensors. That's not a problem. Then if I want to convert these sensor value to a cloud, I need some Wi-Fi module. But in Arduino, I don't have any inbuilt Wi-Fi module. I have to adapt a Wi-Fi module and attach to that Arduino. Then collect the sensor data. Arduino will collect those sensor to Wi-Fi module. The Wi-Fi module will communicate with the cloud wherever you want to store. That cloud, we can just store it. But if I go for any home application, in that case, it will be fine because I have a very big home. If I want to put a box of around 20 centimeter or even 100 centimeter box, I put it will not be a problem. I can go for an extra module and I can use it. But in case the space is a constraint, at that time I have to think whether Arduino is best or not. I can go for Node MCU ESP32 or 8266 because in that we have inbuilt Wi-Fi module. But the Arduino, we have to add extra module, then it will be take a more weight and space also very high. But if I go for that ESP32, that inbuilt Wi-Fi module is there, so the space consumption is less. And at the same time, the weight also very minimal. Based on my application, I have to choose which controller I have been choosing. For the same application, I will take that watch application. In that watch, the space is very important. Okay. In watch, I have many analog sensors. But by using Arduino, I can connect only 6, right? If I want to add some more sensor, I have to add an extra one. And I want to store my physical parameters in a drive. For doctor checkup or my future use, I have to use a Wi-Fi module. Then if I add more modules based on my need, it will make up my watch weight high. If I add more modules at the same time, the power consumption will be more. That will not be practical applicable. So based on our need, we have to choose whether the Arduino or ESP32 or any other controller we have to decide. And nowadays, many advanced controllers are came. In that controller, we have deploy AI model itself. So we no need go for a cloud. Why we go for a cloud? We have store data and analyze data and give output. If I have a controller with AI deployment, I no need go for a cloud. I can do it by itself. Then next thing is communication inference. If I go for a communication, IoT means just take it so wireless communication. We have many options for wireless communication. Bluetooth, Wi-Fi, Zigbee, LoRa, many options are available. Based on our need, again, we have to select which module has to be chosen. For example, I just want to share my smartwatch data to my mobile. Okay. For that case, I don't need to a cloud storage or anything. I just show my daily usage in my mobile. How much distance I watch, those details. At that time, I can go for Bluetooth because when compared to Wi-Fi, Bluetooth will be cost effective. And my phone in one hand and my watch is in another hand. The distance will be very minimal. So I can go for a Bluetooth communication. Then, if my application is, I can't, distance is a main problem. At that time, we can go for IoT module, Wi-Fi or something. The best example is just consider a nuclear power plant. In nuclear power plant, we have to use many chemicals. Those chemicals will be harmful for persons. At that time, the person can't go inside and measure how much temperature inside the boiler, how much pressure inside the boiler. Those things is not possible. So at that time, what they do is they are using RS-232 communication. The operator will be in one room and the boiler and those system specification will be in another room. By using RS-232, the data will be shown in a laptop. They just see it. In Corona time, we can see many news like many chemical plant, some fire accident will be happened, right? Because no man will be go there. Inside, some chemicals are there. Those chemicals reacted with environmental substance. It will cause some explosion. Many news we are seeing in Corona time. Because in that area, they are not implemented wireless communication. We can't just imagine if I have a nuclear power plant, I can see the data, how much temperature inside the boiler, how much chemical reaction. We have many parameters, right? Those parameters, if I am able to visualize inside my mobile, I can control it through mobile also. Okay. At that time, we can avoid many accidents. So based on our requirement, we have to consider which communication protocol we have to use. And that protocol should be supported by our microcontroller also. Because all the microcontroller will not support all kind of communication, right? So we have to choose a microcontroller and what type of signal conditioning circuit and what communication inference we'll use. Everything we have to be considered. Next thing is power management unit. That is very important because if the product consume more power, inside many electronic components are there. Because of the more power, inside components will get heated and the properties will be changed. So we will not get a proper output. So you have to be considered the power consumption based on our application. Whether the accuracy is very important, at that time the power consumption also very minimum. Because if you use more, the power consumption will be high and heat will be produced. Then I will not get a proper output. We already know, right? If a temperature is not constant, the current and voltage fluctuation will be there. The output will not be proper. Then next thing is cloud platform. We have to consider, we have many cloud options are available. From Arduino IoT to Amazon AWS cloud, many cloud options are Azure, many cloud options are available. And in the cloud, we have three important things have to consider. Whether the cloud is private, or public or hybrid cloud. Based on our need, we have to select the cloud. Then the private cloud, yeah, obviously we have a secure system. No one will easily see your data. And public cloud means anyone can access your data, change your data. So we have to consider which cloud we have to choose. And we have some other options. In some cloud, they are providing just an architecture. They didn't give anything. They just allot a space for you. You have to do how, in which the sensor data will be stored, in which the microcontroller programming will be stored. Those things, a model will be stored. Those things will be designed by you one. Okay, that was one kind of cloud. And in another cloud, they give everything. They give us space and they allot a space. They manage your data. Everything will be they consider. So based on our application, we have to analyze which cloud we have to go. Private, public, hybrid. Sometimes we can go for a hybrid cloud. For example, if I are working in an office, at that time, private and public will not be possible. Hybrid will be a best option. Everyone have to store a data in a cloud and management will see that data and do some processes. For example, hospital environment. In hospital, the patient data will be a private. That is very important. So private cloud will be taken. But doctor have to see that data. At that time, that cloud will be a hybrid. Patient data will be secure. At the same time, doctor alone access that data. So based on our application, we have to choose the cloud. Again, in cloud, we have some options. We have some plans also there. They will sell, some amount will be free. After that, we have to pay. Like our Google Drive. Sir, 1 minute, sir. Sir, actually, my phone don't have, based on our application, we have to choose which one we have to consider. What type of controller we have to use, what type of signal conditioning use, what type of communication, and what type of code. It's all based on our application only. We have n number of options because nowadays many commercial controllers are available and many clouds. Each firms give their cloud for free. For example, we have for student friendly and for educational purpose, we have many free clouds like Arduino IoT, Blink, ThinkSpeak. Those are free cloud. In that, they have some easy GUI. So we can easily communicate those GUI. By using those GUI, we can easily control our applications. Then if we go for some professional cloud like Azure or Amazon AWS, at that some amount, we can create our own GUI. In what type our data will be stored, how long our data will be stored, those things we can be customized. Actually, in earlier 2000, the sensor will be used just only for measuring the physical parameter and just converting that to an electrical signal. That's all. But after this, boom of semiconductor and many research, the sensor itself can do many analysis. The sensor can read the data and do some communication, do some computation and can give a final output. Inside sensor itself, we have an analog to digital conversion and everything. It will give the clear output without, we don't need to do any pre-processing like that. Some sensors are available. Then the semiconductor journey. In early 1980s and 2000, the semiconductors will not that much popular. They are used for a very minimal purpose. Mainly, they are used for industrial application. For example, if I want to measure some physical parameters, that time the strain gauge or some other sensors will be used for industrial purpose. After this MEMS, the semiconductor sensor will become commercialized. We can use everywhere, like our home appliance, AC, TV, and Alexa, mobile phone, laptop, everything will be get better because of this MEMS sensor. Because the MEMS sensor will be lightweight, cost effective, and consume low power. So this can be make the sensor commercially available. After this, 2010, the sensor usage, the semiconductor usage will be very high. And because of this kind of sensors, already we discussed some sensors will have many delay and many lag. We can't communicate those sensors with internet or cloud, because in internet we have delay is not correct solution. We have a immediate response in cloud. So this semiconductor based sensor will make it possible. It will transfer the data in a fraction of a second. It will not make any delay or something. So we can use cloud based applications after this invention. Next, in future, the sensors will make zero power. How it becomes zero power means the sensor will try to take energy and power from environment itself. They try to take power from solar, wind, vibrations. By using those signals, they try to convert energy and make use of it without zero. We don't need to put smartwatch for charging. We can use it as like this. By walking, we are shaking our hands, right? Based on that, it generate a power and use for smartwatch application. We don't need to put a charge or something. AI integrated semiconductor will be possible. Why AI integrated is important? Nowadays, every people are using smartwatches, smartphone, and smart gadgets, everything. If everyone using, what happened means the cloud, we can't store that much of data. Even we have more number of them. Even a single person use some MB of data in a cloud. In future, this population will increase. The number of devices also increases. It is not possible to adapt all devices in cloud. And one more important thing is security reason. Even if we are speaking about blockchain and some other technology are available to make our cloud data highly secure, at the same time, cybercrime also increases. So we don't have that much secure when our data is in cloud. So we have to move on to AI integrated devices. Even in microcontroller, we have integrated AI. Why we are using cloud? Mainly thing is, for example, I'm using a smartwatch. My smartwatch can be able to analyze my body parameters like oxygen, BP, per day, how much I walk, and some other physical parameters. It measures and stores. If all the data are by inside my watch, I have a controller or processor are available. Those controllers, what do they just collect the data and send to the cloud. If I put some AI model in that cloud, what happens? The AI model will analyze my data. What is my physical parameter currently and how much distance I walk. Based on those data, the AI model in the cloud can be able to predict after 5 years what kind of disease will affect me. It's really possible. They can predict and tell me by notification in watch. You have to walk this much step per day. Yes, you will get a heart attack within 5 years. Like that, it will intimidate us. Okay. So for doing this process, I can't deploy that AI model inside watch as of now. So what I do, I just collect the data and send to cloud. Inside the cloud, I have a AI model. The AI model will analyze the data and give output. This is a smart watch application. Like that, we can do for many applications. For example, I will take a satellite application. In satellite, we are sending a satellite to space. There are many physical parameters and many things need to be measured, and those sensors will be stored inside the satellite. Two things are possible. One is after the satellite will become, we have to extract those data, and using AI model, we have to find something and will make a result. This will be happen like that. We will give some insight using the AI data. In case I never in this situation, we have to put satellites for 2 times. One, we have to collect the data. After that, we have to analyze the data. Then we have to send the satellite If you want to do some application based on the insight, we have to do it. We have to done the same operation twice a time. But just imagine the satellite will be there, the data will be collected. The data will be sent through some wireless communication through our devices. That by using AI model, they give some insight. Again, we have to comment what to do like that to the satellite. The satellite will do that. But here, the data will be traveled through wireless. At that time, it's there is a high security problem. For medical application and satellite related application, security is very important. We can't take a risk on it. So, if I put AI model inside the satellite controller, the satellite will collect the data in the space and analyze the data, and AI will make the decision, and whatever the further action will be done will all done by satellite itself in the space. We just monitor what happened like that. So the AI integrated controllers, sensors are very much important. That will be the future. We have to move towards on that. Nowadays, we have some controllers, but those controllers are not highly accurate, and whatever the thing we are expect, that is not given. So we are working on that. Next, a semiconductor rate. For example, or before 20 years, the world dominant country will be those who have oil will be the dominant country, right? We know many histories about how the country dominate other countries. If they have oil, that will be the leader like that. In future, even from present onwards, those who have very good semiconductor industries will be a dominant countries in the world. Because nowadays, everything will be a semiconductor. Whatever the app, whatever the application, whatever the device we are seeing, everything is a semiconductor only. Even we are moving from normal automobile to EV vehicle. In EV vehicle, again, semiconductor is a base. So, semiconductor is a very important race running in our world. Nowadays, in a current scenario, only 4 to 5 countries are leading in semiconductor manufacturing. Obviously, one is US, then China, Korea, and Taiwan. These 4 countries are manufacturing their own semiconductor chip. Even India, we have Make in India phones, right? But inside Make in India phone, the semiconductors are used. Those semiconductors will not made by us. The semiconductor will be exported from some countries, US or Taiwan, something. We are just assemble and do other things in our India. We are still Make in India, but it is not 100% Make in India. The semiconductor we use, the chip, semiconductor chip inside system will not manufactured by us. Then we all know our ISRO will be very, very far behind in other research, in space research when compared to other space research organization. Even ISRO also, they are using inside satellite, we need some controller chip semiconductor devices, right? Even ISRO also buying those kind of devices from other countries. Even we are this much far from other countries in space research, we are not using our own product inside our satellite. We are buying and the technology inside it, for example, AI model or something, we are using our own. But the semiconductor device, we are borrowing from other countries. So the semiconductor is very important for our day-to-day life. Whatever the application we are using, semiconductors must. The country who are manufacturing the semiconductor, who are leading the in semiconductor, will rule the world. Now India will step into this semiconductor industry. While starting the presentation, I already told our Union Minister Ashwin Vaishnaw told in one startup mela, he told all youngsters should focus on AI and semiconductor related startup ideas. Then only our country will move forward. The future will be AI, and one more thing is semiconductor. AI, I think we reach more good. Not a full good. Even we are able to compete with the other countries. So, AI, we are doing something. But in semiconductor, we are very backwards. We have just start a beginning step in semiconductors. We all know in recent news we are seen, right? Our first India made semiconductor chip. You are aware of that chip? Do you remember? India made our first Indian made chip. Do you remember the name? Anyone?
Vikram.
Yeah, very good. The Vikram 3805 chip is made by our country in 2025. We all know we are using many laptop, many mobile phone. In all, the chip is very important. But in India, we are not manufacturing it. It's a very shocking news. We are manufacturing our first chip in 2025 only. If you are talking about this chip technology, we have to focus on nanometer. We have developed this Vikram chip with 180 nanometer. 180 nanometer means inside that chip we have 2.5 crore transistors will be there. 2.5 crores is really a large number. That 180 nanometer chip consists of 2.5 crore nanometer transistors. But the sad thing is, in 1990, US created a Intel chip. That Intel chip size is 180 nanometer. Okay, this will be done in 1990. Nowadays, Apple using 3 nanometers chips. In 3 nanometers, the number of transistors inside this 3 nanometer is 2,500 crore transistors. Just imagine the numbers. Inside Apple iPhone, we have 2,500 crore transistors. Our Indian made first microchip will have 2.5 crore transistors. There is a wide gap between it. Only US will make this 3 nanometer chip. Even China also will make 7 nanometer only. So China also begin the US. Now we are stepping our first chip. We are making 180 nanometer for ISRO application. But the best thing is, in 1990 they made a chip with 180 nanometer. We are made the same chip, but that chip will not be used in a harsh environment. It will not give accurate output or anything. We are making this 180 nanometer, but this is for space application. ISRO will manufacturing this. This 180 nanometer will go through all harsh environment. Whatever the temperature, even whatever the noise, everything will be there. This microcontroller will give an accurate result. This is our one of the very biggest success. Then we all know many semiconductor related industries are coming in India. In Gujarat, semicon industry is nowadays in few months back they started, and many crores will be invested in that semiconductor chip. This is the beginning. We have to invest more on semiconductor, and we have to do many research on semiconductor. In research itself, we are doing some designs. In designs, we are very well, but manufacturing side, we are lacking. We just started our step. We have to run faster to accommodate this upcoming technologies. Because in military, in space technology, security is very important. If we are not using our own semiconductor chips, it will be a big problem. We can't buy a semiconductor technology from other countries, because if we buy that, we are not aware of that technology, right? What inside it. So security of data is a very big question. We have to make our own semiconductor chip is very important. Then to move this forward, our government will give many fund on this. Then compared to other startup like AI, health related startup, anything, for semiconductors, they are ready to give many crores for startup fund. First is Semicon India, they are invested 76,000 crore for making a robust semiconductor ecosystem in India. Then this design-led incentive, this scheme will offer many startups. They just try to make the people come into this industry. They are can allow to give domestic companies fund. Why? Because why India is very backward in semiconductor manufacturing is the semiconductor manufactured machines are very costly and the process also very costly. Usually, because of fund only, many people are not confident. If I want to start a company, I just need a good GPU with a laptop is enough. I can do an enormous number of changes in it. But in case if I want to make a semiconductor manufacturing startup, that is not easy. I need a crores of investment. So that is the one of the main reason we are not stepping to that. So government are ready to give many amount. If your idea is very good, we can start semiconductor related industries. We'll have a discussion. If you have any doubt, we'll ask, or any point you want to share, you please.
Participants, if you have any queries regarding the technical session 6, the madam, what she has presented so far, please, this is the time for asking questions, queries.
Actually, I am good in embedded and AI. If you are doing any research or stuck in anything, you may ask. If I have any idea on that, I will help you. If you don't have any idea how to start the work or something, in that also I will guide you. Anything related AI and embedded. Nowadays, in semiconductor based sensor, we all very well know about silicon only used. Apart from silicon, many components are available. Those components will be consume very less power when compared to our silicon, and it will be more flexible. Just imagine if you are using the silicon, our phone, laptop will be very rigid. It will be a flat surface and it will be rigid. If we are move on to some other components, in that the component will be very flexible. We can move on to our phone will be we can just crush our phone like a paper and put it in your pocket. Like that we can move on. In silicon, we have the component will be very rigid. But if you move on to some other components, at that time we can have a flexible devices, flexible laptop, phone, and any other gadgets. It will be flexible. If it's flexible, again, the space will be very less. It occupies very less space. We can store a laptop in a particular place. If I have a paper of that size, I can fold it and place it in even a small place. So we can move on to some other component. Instead of silicon, we can move on to that with the same properties, whatever the silicon does. Silicon will transfer power and conduct electricity on a particular condition, whatever the we program and whatever the circuit we decide, based on that it will done, right? Like that, the same properties should be there, but the component will be flexible. If we move on to that, we can do some other changes in this. Then next thing is, I already told, power consumption. Power consumption, even we are using mobile phone and laptop, everything power is a problem. It will be work good for 1 or 2 years. After that, definitely the power problem will become. We have to change the battery, and inside some components will get fault. We have to change it. If we go for zero power component, those drawbacks will be reduced. Because if I, for example, laptop, if I take, I can give some pressure in keyboard, and if I give some pressure in mouse, if I give that, if they can able to generate electricity from this vibration. Based on that, they can get electricity, and the component inside use a very minimum, and the power usage, we no need of battery, right? Either if you generate and use on it, it will be very good. So the space also again decrease. Like that, we move on to the future.
Participants, do you have any doubts on the technical sessions 6? Please clarify your doubts and queries with engineer Vaishnavi Dinesh ma'am. Please.
If you are,
ma'am, tell me, ma'am. I will share your contact details
yes,
in WhatsApp, via WhatsApp as well as chat box, ma'am.
okay. This design led incentive, this scheme will offer many startup, they just try to make the people come into this industry. They are can allow to give domestic companies fund. Why? Because why India is very backward in semiconductor manufacturing is the semiconductor manufactured machines are very costly and the process also very costly. Usually because of fund only, many people are not confident. If I want to start a company, I just need a good GPU with a laptop is enough. I can do an enormous number of changes in it. But in case if I want to make a semiconductor manufacturing startup, that is not easy. I need a crores of investment. So that is the one of the main reason we are not stepping to that. So government are ready to give many amount. If your idea is very good, we can start a semiconductor related industry. We'll have a discussion. If you have any doubt, we'll ask, or any point you want to share, you please.
Participants, if you have any queries regarding the technical session 6, the madam, what she has presented so far, please, this is the time for asking questions, queries.
Actually, I am good in embedded and AI. If you are doing any research or stuck in anything, you may ask. If I have any idea on that, I will help you. If you don't have any idea how to start the work or something, in that also I will guide you. Anything related AI and embedded. Nowadays, in semiconductor based sensor, we all very well know about silicon only used. Apart from silicon, many components are available. Those components will be consume very less power when compared to our silicon, and it will be more flexible. Just imagine if you are using the silicon, our phone, laptop will be very rigid. It will be a flat surface and it will be rigid. If we are move on to some other components, in that the component will be very flexible. We can move on to our phone will be we can just crush our phone like a paper and put it in your pocket. Like that we can move on. In silicon, we have the component will be very rigid. But if you move on to some other components, at that time we can have a flexible devices. Flexible laptop, phone, and any other gadgets, it will be flexible. If it's flexible, again, the space will be very less. It occupies very less space. We can store a laptop in a particular place. If I have a paper of that size, I can fold it and place it in even a small place. So we can move on to some other component. Instead of silicon, we can move on to that with the same properties, whatever the silicon does. Silicon will transfer power and conduct electricity on a particular condition, whatever the we program and whatever the circuit we decide, based on that it will done, right? Like that, the same properties should be there, but the component will be flexible. If we move on to that, we can do some other changes in this. Then, next thing is, I already told, power consumption. Power consumption, even we are using mobile phone and laptop, everything power is a problem. It will be work good for 1 or 2 years. After that, definitely the power problem will become. We have to change the battery, and inside some components will get fault. We have to change it. If we go for zero power component, those drawbacks will be reduced. Because if I, for example, laptop, if I take, I can give some pressure in keyboard, and if I give some pressure in mouse, if I give that, if they can able to generate electricity from this vibration, based on that they can get electricity, and the component inside use a very minimum, and the power usage, we no need of battery, right? Either if you generate and use on it, it will be very good. So the space also again decrease. Like that, we move on to the future. My session is over. If you have any doubt or anything, I will clarify and I will speak about that.
Okay, ma'am. But the time we have 23 minutes more,
Okay.
I think so. Participants, do you have any doubts on the technical sessions 6? Please clarify your doubts and queries with Engineer Vaishnavi Dinesh, ma'am. Please.
If
Hemlata,
you are,
ma'am? Ma'am, tell me, ma'am. I will share your contact details
yes,
in WhatsApp, via WhatsApp as well as chat box, ma'am. Okay.
okay.
Hemlata, ma'am, shall we conclude, ma'am? I will call you. Are you ready, ma'am?
Yes, sir. I'm ready. I'm audible, sir?
Yes, ma'am. Audible, ma'am. Thank
Okay,
you, Engineer Vaishnavi Dinesh, ma'am, for your excellent and inspiring session. To deliver the vote of thanks for this session, may I now invite Dr. R. Hemalata, ma'am, Head of the Department of Biomedical Engineering, to deliver the formal vote of thanks, please.
Good evening to one and all gathered here. It's my privilege to propose the vote of thanks on behalf of organizing team for this enlightening faculty development program. I express our sincere gratitude to our resource person, Mrs. Vaishnavi Dinesh, for delivering an excellent and inspiring session on semiconductor-based sensor integration for IoT devices. Your insights into practical sensor interfacing, NIMS technologies, and real-world IoT integration strategies have been immensely valuable to our participants. On behalf of management and organizing team and all participants, we sincerely thank you for your time, effort, and valuable contribution to this FTP. Thank you once again, ma'am.
Thank you, ma'am. Thank you.
So thank you, Dr. Hemalata, ma'am, for your thoughtful vote of thanks and for concluding the session gracefully. With this, we have successfully concluded the day 3 of our ATAL FDP on semiconductor for smart system applications in IoT, AI, and next generation devices. We sincerely thank our eminent experts, Engineer A. Madhivanan and Engineer Vaishnavi Dinesh, for sharing their technical expertise and enriching all of us with their knowledge. I also thank all the heads of the departments, Dr. S. Mahendran sir, Professor M. Prishita Arthi ma'am, Professor Sasikumar sir, and Dr. R. Hemalata ma'am for their graceful introductions and vote of thanks. A special thanks to our beloved and respected principal, Dr. V. Sujata ma'am, and faculty coordinators, technical support team, and our enthusiastic participants for their active engagement throughout this session. We look forward to our continued participation of day 4, which will focus on communication and data, featuring 2 more insightful sessions tomorrow. So thank you all once again. Have a pleasant evening. I will share the feedback link about this session as well as queries details on the technical session 6 experts through our WhatsApp group as well as chat box immediately. Thank you all once again. Thank you, Engineer Vaishnavi Dinesh ma'am, for your excellent and inspiring session. To deliver the vote of thanks for this session, may I now invite Dr. R. Hemalata ma'am, Head of the Department of Biomedical Engineering, to deliver the formal vote of thanks, please.
Good evening to one and all gathered here. It's my privilege to propose the vote of thanks on behalf of organizing team for this enlightening faculty development program. I express our sincere gratitude to our resource person, Mrs. Vaishnavi Dinesh, for delivering an excellent and inspiring session on semiconductor-based sensor integration for IoT devices. Your insights into practical sensor interfacing, NIMS technologies, and real-world IoT integration strategies have been immensely valuable to our participants. On behalf of management and organizing team and all participants, we sincerely thank you for your time, effort, and valuable contribution to this FTP. Thank you once again, ma'am.
Thank you, ma'am. Thank you.
So thank you, Dr. Hemalata ma'am, for your thoughtful vote of thanks and for concluding the session gracefully. With this, we have successfully concluded the day 3 of our ATAL FDP on semiconductor for smart system applications in IoT, AI, and next generation devices. We sincerely thank our eminent experts, Engineer A. Madhivanan and Engineer Vaishnavi Dinesh for sharing their technical expertise and enriching all of us with their knowledge. I also thank all the heads of the departments, Dr. S. Mahendran sir, Professor M. Prishita Arthi ma'am, Professor Sasikumar sir, and Dr. R. Hemalata ma'am for their graceful introductions and vote of thanks. A special thanks to our beloved and respected principal, Dr. V. Sujata ma'am, and faculty coordinators, technical support team, and our enthusiastic participants for their active engagement throughout this session. We look forward to our continued participation of day 4, which will focus on communication and data, featuring 2 more insightful sessions tomorrow. So thank you all once again. Have a pleasant evening. I will share the feedback link about this session as well as queries details on the technical session 6 experts through our WhatsApp group as well as chat box immediately. Thank you all once again.